Now, from the previous example, we can deduce a conclusion. Suppose we are given this as x-axis, this as y-axis, and suppose this is the position vector of a particle. That means the particle is at this point. Let this point be A, and we are given the coordinates of this point. Let it be x and y. Then, if we know the coordinates of this point, then we can easily write the position vector without drawing or the diagram. We can write simply r vector as x I cap plus y j cap. In this way, we can simply write the position vector of this particle if we know the coordinates of that point where the particle is lying. Similarly, if we have this 3D space x, y, z, this is the position vector of a particle and its coordinates be x, y, z. Let the particle be P. Then we can write the position vector of the particle is simply x I cap plus y j cap plus z times k cap. In this way, we can simply write the position vector. Let's consider an example. Let a particle is at point 3, minus 2, minus 5. Write its position vector. Then we can simply write its position vector as r vector as 3 times I cap plus minus 2 times j cap plus minus 5 times k cap. In this simple way, we can handle the situation. Now, let's write a note. The magnitude of position vector of a particle is equal to the distance of the location of the particle, distance of the location of the particle from the origin of the reference system. The origin of the reference system. Let's draw the diagram once more, which we have already seen previously. Let this is x direction, this is y direction. To understand this concept, let's draw this position vector, r vector of a particle, this particle, let it be P, and let the coordinates be x, y. Then we can write its position vector as x I cap plus y j cap. Now, let's write its magnitude. Magnitude of r vector is basically square root of x square plus y square, which we have already learned in previous videos in the chapter vectors. Now, let's understand what this really means. The magnitude of this vector is basically this length from the origin to the distance from the origin to the location of the particle, as we have already written, this length, and this can be proved by Pythagoras theorem also. This length is x, this length is y. From Pythagoras theorem, this length is square root of x square by y square. Hence, the magnitude of the position vector of a particle is equal to the distance of the location of the particle from the origin of that reference system. Next, let's see the uses of the word distance. Distance. The word distance is used for two meanings, to denote two meanings. The first meaning is the path length traveled. by a particle. Suppose a particle moved in this direction, then if we are required to find the distance, suppose we are asked to find the distance of a particle moving in this trajectory from A to B, then we have to find the path length of this trajectory. That means we have to determine this whole length in the units of distance, that is meters. Now this can be used for denoting another meaning, which is shortest separation. Shortest separation between two objects. Suppose this is an object A, this is an object B. Then if the question is given that find the shortest separation between A and B, then we have to find this shortest separation, this straight line joining A and B. This is also an usage of the word distance. We should note that in this case the distance word is used for a single particle, but in this case the distance word is used for two objects or two particles. We should also note that in classical mechanics or Newtonian mechanics, we assume an object, suppose a truck, a car, or a bike, a motorcycle, or a wooden block, as a point object. We regard it as a simple point in Newtonian or classical mechanics. By considering it as a point object, we solve the problem further. Next, let us study displacement. We have studied distance as the path length traveled by an object, and the path length is the actual length traversed or traveled by that object along the original path or track. Now we are going to study displacement. Displacement is basically the change in position vector of an object. Here we can write, first of all we can write it is defined for the same object under two different locations. It is defined for the same object. It means we are talking about a single object for the same object for two different locations or two different time instance, or two different time instance. Here we can write it is basically the change in position vector of an object is the change in position vector of an object under two different time instance. Let us suppose let Ri vector, here I denotes initial, Ri and Rf vector, and F denotes final. Ri vector and Rf vector be the initial and final position vectors of an object or a particle or a point object at time t is equal to t initial and t is equal to t final respectively. That means at time t is equal to t initial, the position vector of the particle is Ri vector, and at time t is equal to t final, the position vector of the particle is R equal to R final. Now, therefore, its displacement from time t is equal to ti to t is equal to tf is given as, or is given by the vector delta r vector Here delta denotes the change in this quantity, that means delta change in the position vector. It is our final, that means final position vector minus initial position vector. All these are vector summations and subtractions, not ordinary subtraction. In this way we define the displacement vector. This is a vector quantity as we can see. Since position vectors are vector quantities, their subtraction is also going to be a vector quantity. Now let's see this concept diagrammatically. Let us draw the coordinate system or the reference system first. Let this be x-axis, this be y-axis, and this be z-axis. Suppose a particle is moving in this track. Let at time t is equal to t initial, it is at this point, it means let we denote this point as A, and suppose at time t is equal to t final, the particle is at this point, which is B. Now when it is at position A, or when t is equal to t initial, the position vector is denoted by this vector, which is Ri vector, and when it is at position B, the position vector is denoted by this vector, which is Rf vector. Now to denote the displacement vector, we have already seen it is given as Rf vector minus Ri vector. Now Rf vector and Ri vector is drawn in this way. We have already seen this vector. It will be pointing towards B and the tail is at point A. We can see from triangle of addition also that this is correct. This vector is basically delta R vector. If you see from triangle of addition, Ri vector plus delta R vector should be equal to Rf vector. Ri vector plus delta R vector should be equal to Rf vector. Now we have already seen that delta R vector is Rf vector minus Ri vector. If we place here, we will left with Rf vector. So this is the displacement vector. If we are to find the distance traveled, then we have to if we are to find the distance traveled from time t is equal to t1, t is equal to t initial to t is equal to t final, then we have to find the actual length traveled, that is this length, this whole length. This length, we have to calculate this length. But if we are required to calculate the displacement of this particle from A to B, or time t is equal to t initial to t is equal to t final, we have to calculate the magnitude of this vector along with the direction. We have to denote both the things, that means magnitude as well as the direction, since displacement is a vector quantity. This vector denotes displacement, whereas this path length denotes distance. Let me draw a bigger diagram. Suppose a particle moves in this direction. This is A, this is B, and if we are required to find the distance of this particle traveled from A to B, then we have to calculate the actual path length. It is from here to this way we have to calculate. And from suppose we have to calculate displacement, then we have to calculate only this vector, the magnitude of this vector along with the direction. This is the difference between distance and displacement. Now let's write a few points regarding displacement. The first point we can write is displacement is a vector whose tail is at the initial location of a particle and its head is at the final location of the particle. Here we can see that this displacement vector here, its tail is lying on the initial location of the particle and the head is lying on the final location of the particle. This we have written. Next we have The magnitude of displacement vector denotes the separation between initial and final position. Magnitude of displacement vector denotes the separation between initial and final positions. We should also note that in place of displacement we can only use the term separation. The word separation can be used in place of displacement, although it does not represent a vector quantity, the word separation. So it is better to use always displacement. Now, the next point is displacement is meaningless for a single position. You can write displacement is meaningless for a single position. We should always have two, we should always have exactly two positions to denote displacement. Single position is meaningless to denote displacement. Now, let's write an important point. The actual path length or distance in terms of physics of a particle may be equal to magnitude of displacement or may be greater than magnitude of displacement. The actual path length, that is distance, can never be greater than the magnitude of displacement. From this diagram we can easily see this concept. Suppose this is the trajectory in which a car is moving. Let this car moves from point A to point B. Then its distance is denoted by this actual path length traveled, and its displacement is denoted by this vector. We can easily see that the length of this vector will be always less than this actual path length. Now, it is also possible that the actual path length, that is distance, may be equal to the magnitude of displacement when in case the particle is moving in a straight line without reversal of motion. That means it is not changing its direction, it is not turning back, it is always moving in this direction, and it moves from point A to B. It is a straight line path. Now here we can see the actual path length traveled will be equal to the magnitude of this displacement vector. That means the actual path length traveled or distance may be equal to this displacement, to the magnitude of displacement, or it may be greater than the magnitude of displacement, but it is never less than the magnitude of displacement. So we can write path length or distance is always greater than or equal to magnitude of displacement. And if we are given that path length is equal to magnitude of displacement, then in that case we should understand that the particle is moving in a straight line without changing its direction. Because if it changes its direction, we can see, let a particle moves in a straight road, first of all going from point A to B, then it again moves from B to point C. This point is C. First of all, it moves from A to point B, then it comes from B to point C. Then its displacement vector will be this vector, initial position to final position, but its distance traveled will be this much, AB plus BC. Distance traveled will be AB plus BC, but the magnitude of displacement is this AC vector, so magnitude will be AC. Here, although the particle is moving in straight line path, both this distance and magnitude of displacement are not same, since there is a reversal of motion. So for this equality sign to hold, there should not be reversal of motion, and the particle should always move in a straight line in a single direction. That means in a single direction.